The physics of the selective interaction of short-pulse laser irradiation with inhomogeneous areas in condensed matter is a perspective important both in the field of condensed matter physics and in the field of materials science. We experimentally established the potential for the simultaneous enhancement of hardness and resistance to surface cracking in a titanium alloy due to selective laser irradiation. A physical model is proposed for the healing of nanopores situated in the surface layer of the sample. The increase in nano-hardness of the laser-treated surface by 1.5 times or more was accompanied by an increased resistance to cracking. The physical phenomenon underlying selectively laser-initiated pore healing at the nanoscale is determined by the specific distribution of isotherms and the shock compression of the material, which is influenced by both laser heating and the configuration of the nanopore system. Laser processing was carried out using the LS-2136 laser system. The scheme illustrates the focusing of the laser beam. The positioning system was configured in such a way that the surface of the sample was processed in several stages. The first stage allowed for the creation of a system of circular areas. The centers of these circular areas were situated at a distance of 1.5 diopters equals 150 plus or minus 2 microns from each other. The second stage was carried out with a shift relative to the last melting zone at a distance of 100 microns. Similar matrices were formed at the third and fourth processing stages. Microphotograph of untreated surface and microphotograph of the irradiated surface. Visible areas of laser melting have the shape of circles with a diameter of 100 micrometers. The nano-hardness value for the untreated sample was 4.32 gigapascals. After selective laser treatment, the nano-hardness value was 6.22 gigapascals. Microhardness Vickers hardness and the mathematical expectation of the probability of crack formation after loading, using the Vickers pyramid on the titanium alloy VT18U, before and after treatment with a series of laser pulses. For the untreated surface, the mathematical expectation of the probability of crack formation after indentation was 0.2 at F equals 0.49 newtons and 0.55 at F equals 4.9 newtons. There was no surface cracking on the laser-treated surface after local loading using the Vickers pyramid in the range loads of 0.49 newtons and up to 4.9 newtons inclusive. Figure 1. A model of the geometry of the triangle pore system. Points 1, 3, and 5 are the boundary areas of the material adjacent to the upper part of the pore. Points 2, 4, and 6 are the boundary areas of the material adjacent to the lower part of the pore. Figure 2. Changes in temperature on a straight line, along the height of the triangle ABC. S is the distance to the sample surface. The discontinuities on the dependency curves correspond to the pores. Pore healing under the action of a compressive force. The red dots show isolated healed areas.